Hi, this is Mr. Denny, and today we're going to do just a few beam deflection problems. So let's go ahead and look at the beam deflection equation. So we say that the amount of deflection, which is this delta, is equal to the force times the length cubed of the beam divided by 48 EI. Now, I just want to take a moment and look at some of the things here. Some of them are kind of obvious. Obviously, the more force we have, the more the beam's going to bend. But also, the longer the beam is, that's this cursive L here, the longer it is, the beam bends more too. And it makes sense, because if we have a short beam and we have a force on it, it's only going to bend a certain amount. But if we have a longer beam, even if we have the same amount of force on it, it's going to bend more. And you experience this in real life. If you've ever broken a stick or like a pencil in half, and then you take one of those halves and try to break it in half again, it's a lot harder to break. And eventually, by the third or fourth time you do it, it's pretty much impossible. And that's because your length keeps getting shorter. And length is a big part of how much something bends. See, it's length cubed. All right? Now, on the bottom of the equation, the stuff down here, the larger these numbers are, it actually makes it bend less, because as the denominator down here increases, naturally our deflection would decrease. So we have E, which is our modulus of elasticity. This is measured in pounds per square inch, and usually, it depends entirely upon the material, but we're usually looking at wood being around 500,000 to 2 million. Steel is about 30 million. Titanium is like 45 billion. Like, it's usually a pretty substantial number, usually in at least the hundreds of thousands, unless you're looking at something like, rubber or something like that. The I value is based on the shape of the beam that's bending. So if I have a beam that looks like this, and I apply a force to it, the I value is actually based on this shape. That's called our cross-sectional shape. And what we're going to look at is this dimension, which is called the base. Now the base is perpendicular to the force. And then we'll have another dimension called the height. And this is actually going to be parallel to the force. All right. If the force was actually coming in, let's go ahead and make that red so it's obvious it's different. If the force was coming in at a different direction, if it was coming this way, this side would now be the base, and this side would actually be the height, because this side is now perpendicular to the force, and this side is now parallel to the force. So we got to kind of think about how the force is coming in so we can determine which side's the base and height. Once we've done that, we can write our equation for our moment of inertia. And our equation for moment of inertia is 1/12 base height cubed. All right? Now, base is inches, height is inches, so we have inches times inches cubed. The unit here is actually going to be inches to the fourth, which is a kind of strange unit. 1/12, I want to make sure it says that. And the reason that we have this weird fraction here, this 1/12, actually has to do with calculus and integrating numbers and things like that. We're not going to get into that here in this class. I don't think many of you guys have had calculus yet. So let's go ahead and look at the last part of this equation. So we said that the deflection was the force put on the beam times the length cubed over 48 EI. Now, you may wonder where this 48 number comes from. Like, why is it 48? And actually, this number can change depending on how you hold the beam. Now, I only need you to know two types. If I have a beam that's called simply supported, which means it's held on each end, and we apply a force in the middle, the number you're going to use is 48. All right. The only other type of beam we're going to use is what we call a cantilever beam. which is where I have a beam and it's held just at one end and we put the force at the other end. In that case, the number we're actually going to use is 3. 2 exclamation points. All right, so, and the reason for that is this beam will bend significantly easier than this beam will. And how do we find these numbers? Why is it 48? Why is it 3? We actually find them through testing and experimentation. So those are our numbers. So that means our two equations are either going to be with 48 on the bottom, or if it's a beam that's only held at one end, it's going to be force length cubed over 3 EI. All right, so we'll use one of these two equations depending on how the beam's held. Like we said, right here, this type of beam, we'll use a 48. This type of beam, we'll use 3. All right. There are a lot of other ways to hold beams. There's a lot of other numbers that can go down here. But for our purposes for this class, those are the only two we're going to look at. So let's do a couple quick practice problems. So let's say we have a factory and there's a beam on the roof. And we'll say this beam is 4 inches tall and 2 inches wide, and it's made out of steel. So we'll say our modular elasticity is 30 million psi. And we're going to put an air conditioner on the beam to help cool down the factory. All right, our beam, we'll say, is 15 feet long. All right. We want to know what the heaviest air conditioner is. What's the most force we can have if this thing can't bend more than, let's say 1.5 inches. So let's look at our equation here. We'll say our deflection is the force length cubed over, and what kind of beam is this? Notice it's held at both ends, so we're going to use 48 EI. So we want to find a couple of things first. So we want to figure out what we have here. We know our deflection. It can be 1.5 inches. We don't know the force yet. We're going to want to solve for that. The length is 15 feet. However, notice everything else is in inches. This is 2 inches, this is 4 inches. Remember, when we find our moment of inertia, that I value, it's in inches to the 4th power. So we want to actually take our 15 feet and convert it to inches. So I'm just going to multiply by 12, and instead of saying 15 feet, I want to say 180 inches. Okay? We have 48 as a constant. Our E value is based on the material, which is steel, which was 30 million psi. And our I value, remember we know how to calculate I, it's 1/12 base height cubed. And in this situation, the base is going to be this 2 inches, and our height is going to be that 4 inches, because the 2 inches is perpendicular to the direction of the force, and the 4 inches, this measurement, is in the same line as the force. So it'd be 1/12 2 times 4 cubed. All right, so let's go ahead and do that. And I got 10.7. All right, now we know all of our values except for force, and that's what we're trying to find. So we're going to go ahead and rearrange our equation. So I'm going to multiply both sides times 48 EI. So delta times 48 EI equals force length cubed. And I want to get rid of this length cubed term, so I'm going to move it to the bottom of the fraction, length cubed, and there's my force. And I can go ahead and plug the numbers into that. My delta was 1.5. Then I had a 48. E is 30 million. And I was 10.7. And my length was 180 cubed. All right, you have to forgive me. I'm sure you all can use calculators. I don't have one with me here, so you can go ahead and type that in. A little bit much for me to do in my head. All right, and that will give us how much this beam bends. All right, let's look at one more practice problem here. Let's say we have a diving board. All right, and we have a force on the end of this diving board. Let's say we have a person who's 200 pounds. We'll say our diving board is 8 feet long, 12 inches wide, and 1 inch tall. We'll say that the diving board is made out of some sort of plastic that has a modulus elasticity of 600,000 psi. We want to know how much is this diving board going to bend. So when it bends down, what is that deflection? All right, so our equation, deflection equals force times the length cubed over, and now is this going to be 48 or 3? Is it held on both ends? No, it's just held on the one end. So this is a cantilever beam, so it's just going to be 3 EI. So we want to find I is 1/12 base times height cubed. In this situation, since the force is coming down, our 12 measurement this way is perpendicular to it, so that's our base. So that's 1/12, 12 times 1 cubed. And we can see that that's just going to be 1. So we have I, we have E, 3 is a constant. The length we said was 8 feet. We don't want to use feet, so we're going to rewrite that as 96 inches. And we have a force. So we're going to go ahead and plug this in here. Our deflection is 200 pounds times 96 inches cubed over 3 times E, which was 600,000, times I, which was just 1. And we'd plug that all in, you'd put it in your calculator, and get an answer. So basically, all these problems are going to follow the same kind of pattern. So determine what number is on the bottom. All right, so it's going to be 48, the beam's held at both ends, or is it going to be 3, where the beam is just held on one end? All right, so figure out what that is. 2. Make sure everything's in the same units. So if you have feet, convert it to inches. All right, we want to have everything in the same units. If we're using pounds per square inch for our E value, we want to make sure we're using inches to the 4th power for our I value, and we want to make sure they're using inches for our length. So make sure we're all in the same units. Rearrange the equation for the unknown. So if I had deflection is my force length cubed over 48 EI, and I wanted to find, let's say my E value here, I want to rearrange this. So I'd say for that particular situation, E is going to be delta 48I over force length cubed. All right, so rearrange the equation for the thing you're trying to find, and plug in the values, do math, get an answer. All right, so that's kind of the same pattern you're going to follow for all of the problems, and that should get you where you need to go. All right, good luck on your practice problems.